Hello, everybody, and welcome back to another Mr. Farney Earth Science video. In this video, we're going to start our discussion about the Earth-Moon system by focusing on, the moon. It's up there. It's the big bright thing you see at night sometimes. Looks like it changes phases over a period of time. We're going to talk a little bit about, the moon is, the history of the moon, the formation, and then get a little bit into kind of those phases, and then talk a little bit about the mechanics behind eclipses, and then close it out. So we're going to start off with just, little brief background information about, us exploring the moon. We've used telescopes and space probes to help us kind of begin our understanding of what's going on the moon. Our space probes, including the Lunar Prospector and Clementine, were some of the first space probes that we used. Sputnik 1 in 1957 was one of the first artificial satellites that was deployed by the Russians to do some space exploration. It was the first artificial satellite that orbited the Earth. It started the Great Space Race. For manned missions, the Vostok in 1961 was when we had our first human that we put into space. And then we had the series of the Apollo missions that were dedicated to get to the moon, to land on the moon, to study the moon, and all that jazz. So a whole bunch of different information there about what we've used to explore the moon. Now, first couple things here, if I scroll ahead here, that make up the lunar surface is we have light color, dark color. The highlands are composed of light colored rock, which is the lighter shaded areas of the moon. It's heavily cratered, as you can see in the picture here, a lot of impact things from the early formation of the moon and kind of its early life cycles when most of those impacts happen, when there was still a lot of debris floating around in that early solar system before things kind of settled down, cleared up, and we don't have nearly as much impact as we used to. That's the highlands, the lighter colored area. The Maria, or Maria, if you will, are the dark colored areas. It's smooth and it reflects little light. We can see that there. One of which is like the Sea of Tranquility that we talk about one of the prominent features on the moon. These dark areas, it's dark solidified lava. And as we've, excuse me, discussed in class, if we have evidence of lava somewhere, it means there's probably one point in time, either plate tectonics or some type of magma or volcanic activity going on. So since there are lava rocks on the moon and it's no longer, volcanically or tectonically active, we use that as evidence that one point in time in the past, that was such a thing. So our high areas, the highlands, the light colored, the Maria or Maria, those are the dark colored areas of the moon. Impact craters, like I was saying, form when objects from the space crash into the lunar surface. And when it hits the surface, it kicks up a whole bunch of dust and dirt that we call ejecta. It's a material that's blasted out during impact and kind of the surrounding crater of the area. So impact craters, again, most of these formed way in the way back machine when the Earth first got the moon. And then that moon was, I wouldn't say blocking things from hitting the Earth, but it definitely helped kind of cure some of that material that was on a course for Earth. So thank you, Moon. You're a good friend. All right. Other types of lunar features, we have craters, which are bowl-shaped depressions. Again, most formed 4 billion years ago when leftover debris from our formation of the solar system was flying through space. So we now know from the nebula theory that we learned about in the previous section that the last step of the nebula theory was we had like a whole bunch of remaining debris and dirt and rock material left over after protoplanets become planets. And a lot of that material becomes moon. The other materials are kind of, float around, become our larger features of our solar system, like the asteroid belt, the Kuiper belt, maybe some dwarf planets if it's big enough, random asteroids. But that leftover material that didn't become part of the planets, they began impacting either planets that did exist or some of their moons. So these craters or bowl-shaped depressions came from those impacts about 4 billion years ago from leftover materials. Rays, if we can see here, it's like the really long white streak patterns coming out of the crater area. There's streaks of materials that were disturbed during impact. So again, ejecta, maybe really long ejecta, made these rays on the surface of the moon as it kind of streaked along with it. Rilles or Rilles, however you want to pronounce it, they're long, deep channels that run throughout the Maria. So right here, running kind of perpendicular across the picture, or sideways across the picture there, that long, deep channel that was once a lava channel from when the moon was volcanically active. So again, that channel right there probably has home to some lava rocks, and it's probably about 4 billion years old also. So really good Bremen and a piece of evidence that the moon was at one point in time tectonically or volcanically active. Some 4 properties that make the moon very unique. One, it's one of the largest moons compared to its planet that we have in the solar system. The moon is very large compared to some of the other moons in proximity to, how big Earth is. It's solid, rocky, while most of the moons in the solar system are, primarily made out of a lot of ice. It orbits a much further from its planet than other moons. A lot of the other moons are a lot closer. Our moon is a lot further out there. And another unique property is a very similar composition to Earth. It is mostly silicate materials that make up the rocks. Highlands are made of different types of breccias. The Marias are mainly basaltic. So again, a lot of the similar characteristics that we see here compared on Earth, where, our lava material is very basaltic and things like that here on Earth, especially where we have new volcanoes and new lava being made on our planet. So very similar composition to Earth that we find on the moon. It's very unique. Here's a very brief history of the moon. I know we're going to cover some articles in class discovering like space travel and stuff like that, but the specific to the moon, the lunar surface is very old. Rocks that we have collected from, the Apollo missions that landed on the moon that we've brought back, they've been dated to be between 3.8 and 4.6 billion years old. It's made up of loose, ground up rock that we call regolith. Okay, loose ground up rock that we call regolith. The moon has a layered structure. It has a crust, an upper mantle, lower mantle, and a core, very much like the Earth. So that means that, in the early formation of that moon, when it, after it possibly impacted the Earth, flew out, and it began cooling, the different types of elements that make up those different layers, it began differentiating with the more denser elements kind of migrating toward the center to the core of the moon, and the lighter silicate elements kind of drifting toward the outer crust. How do scientists know this? Well, they knew this using seismometers. It's kind of the same way that we know the different layers of our material on Earth are. The P and the S waves, different types of waves are going to be able to go through different types of materials. So this is how we know the moon is structured. We use similar mechanisms on the moon that we've used on Earth to figure out what's going on at the different layers. For the first 800 million years or so of the moon's life, it was heavily impacted by craters, creating those highlands and the Maria underneath it. After those impacts kind of cooled and stopped, the lava from the moon's interior came up and filled the low areas from those impacts, creating our smooth Maria. There were ancient lava tubes that had collapsed that caused those rallies, those like long, thin tube areas throughout the Maria. So those were once ancient lava tubes. So the first large portion of the moon's life was extremely hectic between all of these impact craters being created, the lava coming up from the inside of the moon, the collapse of these ancient lava tubes. So the early life of the moon was very, very hectic. There is almost no Maria on the far side of the moon. On the side of the moon that does not face us, not a lot of Maria. Scientists predict that the crust is thicker on that side, which is very possible. On Earth, there are different thicknesses to the crust depending where you are, going around the planet itself. So they believe that because it is thicker on that side of the moon, that it was very difficult for the lava to reach the surface. So that's why it's predominantly on the one side of the moon that faces us. Again, we've already spoken about this. Scientists use seismometers to measure the strength and frequency of, look at this, we call them moonquakes because we're not on the Earth. Earthquakes here, moonquakes up there. That's kind of a fun thing. There's no volcanoes on the moon. There are no magnetic fields. In the mountains, they weren't formed by tectonics on the moon. So it was majority impact craters and then lava just kind of welling up from inside of the moon. So the moon doesn't have volcanoes or tectonics there or a magnetic field. So while there are some characteristics that make the moon similar to the Earth, there are kind of these slight differences between the two. Now, the last thing that we'll speak about here in this video is that there isn't just one clear theory about how the moon formed. There's a couple leading ones. First one is the capture theory, is that the moon was formed somewhere else in the solar system and then pulled in by Earth's gravitational pull, like in the last step of the nebula theory. Issue with that is it doesn't explain why the composition is very similar. So capture theory, it was formed somewhere else, and then we grabbed it as we orbited around the sun. Condensation theory is that the moon and the Earth were formed at the same time from the solar system nebula material. Again, we're going from like planetesimals, protoplanets, and then the remaining debris form other things. But then it kind of gives us this question: why are they two different sizes if they formed about the same, roughly the same time? Colliding planetesimals theory is that leftover planetesimals collide and form the moon. And then, question is, well, why didn't these strike the Earth? The leading one, and it's one of the ones that I like the most, is the Giant-Impact Hypothesis, where the moon formed when a Mars-sized body, so a very large protoplanet, struck the Earth about very early on in the Earth's life cycle, within the first several million years of Earth being, in existence there. A Mars-sized body struck the Earth and fragments were ejected into orbit around the Earth, and they eventually kind of coalesced and combined to form the moon itself. So personally, I like the Giant-Impact Hypothesis as, a reason that we have the moon. Other scientists might lean to, some of the other three that we have here. So just be aware that there isn't just one clear explanation for how the moon formed, just kind of leading theories about possibly how it did form. And that's where we're going to stop this video. When we come back and talk in the next one, we're going to go through and talk a little bit about the different phases of the moon, how that works, and then maybe squeeze in a little talk about eclipses and how they work too. So thank you all for watching. If you have any questions, please let me know. If not, have a good rest of your day, and I'll check you out next time. Bye-bye.